everyone, let's get started. Any questions about Lab 2? Any issues? Okay. Yes, yeah, you can demo it whenever is convenient. If you just set up a time during class with the TA or outside of class, if you want to make an appointment. You won't receive a grade till you demo it, but the submission time is based on when you uploaded it to Blackboard. Blackboard. Okay, so today we're going to, I want to review a few things I talked about last time about sequential logic, clock logic, and then we're going to get into the RISC microarchitecture so we can assign the next lab. So last lecture I talked about the always statement, which is the same as the VHDL process. With the always statement, at least in terms of synthesizable Verilog code that you're writing to put on a chip, it can serve two purposes. One is to create complex combinational logic, like some of you guys did with your 7-segment decoder, where you used an always statement to create an if-then-else or a case statement. Another use is for clocked logic or sequential logic. So there's the thing about the always statement is when you compile the always statement, if it has memory in it or sequential logic, that is implied through the way that you write it. At least when you use the regular always, just this plain old always statement. Of course, they have those variants, always FF and always COM. But so traditionally, if you have an always statement and you specify a sensitivity list, but there are inputs inside the body of the always statement that are not in the sensitivity list, then the logic that's generated from that will automatically imply some kind of a memory. So an example is if you say always at pause edge clock, A gets B, B is an input. B is treated as an input inside that always block, but it's not part of the sensitivity list, so that will automatically imply logic. And in this case, it's going to create an edge-sensitive memory element, a flip-flop or register. Another way, though, is if you have always at star. Now, always at star means that anything that's an input, anything that's treated like an input in the always block if there's a state change of anything that's treated as input, it'll activate the always, right? You would think that this would create combinational logic, always. But in this case, I have if A equals 1, then B is assigned to C. But the problem is, what happens if A is not equal to 1, right? So what's happening here is that I'm activating the always when any inputs change, but I don't change all of the outputs depending on how the if statements are resolved, depending on the control flow through the always statement. You guys with me? So I didn't change B if A doesn't equal 1. I only change if it equals 1. This will also create a memory element called a latch, even though it doesn't look like it should. Now on an FPGA, you generally want to avoid using latches. You want to avoid this type of memory because on an FPGA there are no latches. There's no transistorized latches in the fabric. You just have flip-flops and RAMs. I'll talk about RAMs in a minute, but those are the only two memory elements you have is flip-flops and RAMs. So in order to create the behavior of a latch, you have to, the synthesizer has to somehow create a latch with what it's got on the FPGA fabric, and that turns out to not be very efficient. So generally, if you have latches in an FPGA design, that's usually a bug. And the bug is you forgot to assign all possible outputs for every possible control path through an always, if you have an if statement. Does that make sense? Okay. So, but latches are a thing, though. I mean, so for instance, let's look at these two cases. So you have a clock signal and you've got a D signal. So And then you've got a latch, which would just be written as I had it, although I changed the names here. Instead of A and B, I put always at star, if clock equals 1, then Q gets D. That's a latch. And the corresponding flip-flop is always at positive edge clock. If clock equals 1, Q gets D. Okay? And actually, this is redundant. If clock equals 1, it should just say if Q, it should just say Q gets D there. So let me change that. Sorry. This part is redundant. It would normally be written as, it would just say, this is your flip-flop code. Okay, you guys with me? Okay, so basically what happens then is in a latch, whenever the clock is high, then whatever's on D will just propagate to Q as long as the clock is high. So basically Q is always equal to D whenever the clock is high, but then when the clock goes low, it'll capture whatever was in Q and hold it, right? So if you look at its waveform, you've got D changes once here, once here, once here, once here, and once here. So if you look at D, there's 1, 2, 3, 4, 5 transitions of D. Clock is high for that first transition. You see that first transition, clock is high, which means it's kind of like the gates are open there. So while the clock is high, the gates are open, so the D propagates out to Q. So when that D goes up, Q goes up. Likewise, when that D goes down over here on this side, the Q goes down, right? Because clock happened to be high when that happened. And then when the D goes back up, the Q goes back up because once again, the clock is still high. Now, when you get over to this part, the clock is low. And so when that D goes down and back up, you don't see that reflected on Q because Q is locked in because clock is low, right? So because clock is low during this falling edge and this rising edge of D, that's not reflected on Q. So in other words, long as the clock, when you have a latch, as long as the clock is high, stuff passes through. D passes through to Q. When clock is low, it locks in the bit that's stored, right? Now on a flip-flop, it responds only to the rising edge of the clock. So the first rising edge will cause Q to go low because D was low on that rising edge. The next rising edge, Q was high, so that causes, D was high on the next rising edge here, so that samples that D being high and then the Q goes high. You guys with me? Okay, but like I said though, you want to avoid latches on FPGAs. So whenever you have an if statement, as I mentioned, a lot of times this turns out to be an unintended behavior. You'll have an if statement like this and you'll just forget to create a default assignment for B, right? So you can either add an else to this if, or you can assign B to a default value before the if statement and then reassign it potentially if the if condition is true. And remember, in an always statement, only the last assignment actually takes effect, right? So if you assign all, so this will happen, let me give you a more concrete example. In your control unit, in your CPU, you're going to have this big, complex, nested if then else statement, right? So you're going to have an if statement that looks at the function code and the opcode of your instruction that's currently being executed, and then you're going to use that to generate all of the control signals to execute the instruction. At the beginning of your control unit, at the beginning of that, or I should say right before that if statement, you want to have default assignments for all the control signals. Because if you forget even one, if you forget to initialize a control signal, then a latch will be created for it, right? Now, what's essentially happening there is if the latch is created, what it's doing is setting up a memory element to retain the prior output. Whatever the output was before the always statement activated, it needs to retain that, so it has to create a latch for that, right? But you don't want the control unit to be a latch. You want the control unit to be a combination of logic circuit. Control units are lookup tables, basically. They take the function code from the instruction and any kind of other control bits in the instruction, function code and opcode and whatever little control bits are in the instruction word, and it converts those to what some people call microcode or control signals that go out into the CPU, right? That should be a combinational logic circuit. It should not be a latch. Now, I also mentioned in class that if you say always underscore FF in the code, that tells the compiler that you're intending to create a flip-flop, or if you say always underscore com, you're intending to create a combinational. So if you make this mistake, like let's say this is an unintended latch, if you had just put always underscore com here, then the compiler would then have caught that and generated an error, right? And said, hey, that's not combinational, you made a latch, right? But this is kind of like the generic always. This is the Verilog always, whereas the always com and always FF are things they added in SystemVerilog to try to, because of this, I mean, they were in response to these types of errors, right? Okay, does that make sense? Okay, okay, so we talked about this. Here's an example of always underscore, in this case, always underscore FF. Again, the underscore FF just tells the compiler it's your intent to create a flip-flop. Pause edge clock, this basically just is a very simple flip-flop. There's no enable, there's no reset. And essentially what it's doing is converting, it's just delaying whatever comes in, whatever's coming out of Q is essentially whatever's going to be going in the D in the previous clock cycle, right? So it just shifts, it just delays this D by one cycle, right? And I said flip-flop, I should have said register, because in this case, notice that these are 4 bits in and 4 bits out. So this is kind of like having 4 flip-flops in parallel, but these are usually called a register in this case, right? But this is not to be confused with like a RISC-V register. This is it's confusing. There's RISC-V registers, which are like numbered registers in the assembly code, and then there's these types of registers, which are just flip-flops essentially, multi-bit flip-flops, right? Does it make sense? Okay. I mean, it doesn't make sense, but it's just one of the weird naming things. Okay, you can also create, you can put additional code in that always to reset either synchronously or asynchronously. Synchronous is when the reset is not part of the sensitivity list. Asynchronous is if it is. You should use asynchronous on an FPGA. And I actually didn't know this until, or at least on the FPGA we use in this class. I didn't know this until a week ago. But as it turns out, we were looking at the timing analyzer, and the actual flip-flops that are in the FPGA fabric have an asynchronous reset. So if you put a synchronous reset in your code, it doesn't actually use the reset input on the flip-flop. It combines the D with the reset. In other words, it bolts extra logic around here to create this synchronous reset, which in the case of Alex's design, when he took this class in the fall, it created a critical path, worst case path delay. In other words, it was the bottleneck for his clock speed, right? So you should use an asynchronous reset just because that's the most efficient way for the FPGA. Okay, now here's an example, by the way. So this is actually a better example of this. So in this case, we have, you could have a flip-flop with an enable input, right? In this case, this enable is not like reset. Enable just allows you to ignore the rising edge of the clock, right? In other words, you can retain values in the flip-flop across multiple clock cycles if you disable it. So this is the enable signal going straight into the flip-flop. Of course, you could also create the same effect by creating a mux here and feeding back the D, so when enable is 0, or feeding back the Q, so when the enable is 0, it keeps feeding Q back into D, right? So this is an example of where if you don't have primitive support built into the actual flip-flop circuit, you can bolt logic around it in order to create the same behavior, right? And that's what the tools do to create a synchronous reset. Okay, yeah, so here's an example of having reset and an enable. This is just implemented with an if statement inside a clocked always statement. Notice here there's no begin and end because this if statement is just one statement. So it counts as one statement. So you don't need a begin and end. If you have multiple statements in that always, you need to have a begin and an end, right, for the always block. Okay, I already talked about that. Okay, so you can do other things. So you're not limited to just creating flip-flops or registers or latches. You can create kind of arbitrary sequential logic. So in this case, I'm creating an up-down counter. So you have an always block, clocked logic block, and if there's in this case, there's a synchronous reset, which resets the count, which is a 6-bit value, to 0. Otherwise, if you're not resetting and you get a rising clock edge, you increase the counter by 1 if the enable up signal is asserted, and you decrement the count if the enable up signal is not asserted and the enable down signal is asserted. And if neither one of them are asserted, it'll hold the count, right? So this allows you to count up, to count down, or to hold, right? Now, if enable up and enable down are both asserted, it's going to go up because that's the priority list in the if statement, right? So if they're both asserted, it's going to count up by default. If only down is asserted, it'll count down, and if neither are asserted, it'll hold, right? But the point is you can create these kind of behaviors inside the clocked circuit. So in this case, or clocked block. So we don't have a Q input here. We could add a Q input to allow us to initialize the count to something other than 0, but then we'd have to have an initialized control bit and a value that you want to initialize coming in. Yes?
Yes. You said like the if statement, the else if the first statement will be given priority in that case if
Yes.
both of them are
Yes.
enabled. But I thought like going through the Verilog, the last statement gets the priority.
Well, in the case of the last assignment gets priority. That's correct, the last assignment. But in this case, the control flow will just go into this clause. If enable up and enable down are both asserted, it's going to go into this clause, and it's not going to execute this one with the enable down, right?
So sequential logic makes sense.
Yeah. So and this is sequential semantics. Yeah, this is one of the exceptions. So I always say that Verilog has concurrent semantics, but within the context of this always block, they use sequential semantics internally, right? But when this is synthesized, what you're basically doing is you're creating a truth table from this internally, a next state table that is following the semantic rules of the if statement. But in reality, it's just what ends up becoming it's just a shorthand way to build a truth table for the next state logic. Right. Okay. Okay. So here is an example. There's this website called chipdev.io, in which supposedly they have gathered interview questions from the big semiconductor companies like Intel and NVIDIA and Apple. So if you go for a job interview, they'll often ask you to write small Verilog designs to implement something. And somebody took some of those, I guess, from, someone interviewed and they told this guy, and he put these questions on this website. So I think it's kind of cool. They also have on this website a way that you can answer these questions, and they have a built-in Verilog simulator, so you don't have to use Questasim like we do. So this question, here's an example. It says build a circuit that pulses D out, which is an output from this module, 1 cycle after the rising edge of D in, defined as writing a single cycle 1 is shown below. When reset is asserted, the value of D in should be treated as 0. So basically, all you have to do, there's 2 things you have to know to do this. The first is how do you detect a rising edge? This is an edge detector. We want to find the rising edge of D in. To do that, you create a clocked block, and you keep track of the last value of D in, like a delayed form of D in. And then if you compare the delayed form of D in to the current value of D in, if the old value was 0 and the current value is 1, then that would indicate there was a rising edge, right? That's how you build an edge detector. So you basically just create a flip-flop for D in. Okay, so, and the other part of this is you have to pulse, you want to have this D out pulse for 1 cycle, right? So notice that D in is actually high for 2 cycles here, but I still only pulse this for 1 cycle, right? So I went and put in my answer to this, and you know, you can hit a button and it tests it for you automatically. They have a test bench actually built into the website. And so this was my answer. I don't know if this is the best way to do it, but so there's the module line over there, and then I declare this thing called internal signal called din old, and then there's just one clocked always statement. I say always at pos edge clock if reset n tilde reset n, because the n indicates that it's active low logic, meaning when reset is 0, that means we're resetting. So if we're resetting, I'm going to set d out to 0 and din old to 0, right? Otherwise, I am going to always delay din by one cycle by just setting it to be, by setting din old to be din, right? Now, because this happens inside of this clocked always statement, the din old will always be one cycle delay of din. So down here, I plotted, I put this into QuestaSim, and I plotted these signals. So you can see din is here, right? There's your two cycles, two cycle long pulse, I guess, right? And din old is the same, is just a reflection of that, but it's phase shifted by one cycle to the right, meaning it's been delayed by one cycle, right? So din and din old, same value, just shifted in time, right? Okay, then I have some other logic in there that says if din old is 0 and din is 1, that's the edge detector. That will detect a rising edge, in which case d out is 1, and otherwise d out is 0, right? So now you might notice that there's something a little weird going on, because the din old and din, I think that probably makes sense. That's easy to understand. But the weird thing is, notice how after the rising edge, there's a one cycle delay before I actually get the d out pulse, right? It's not instant. It takes a cycle for it to even recognize that rising edge. Why is that? Well, the reason is because the if statement that detects the rising edge is also in the always block that's clocked, which means that there is also a one cycle delay to detect that edge, right? So basically I combined into one always block the delaying of din, right, which is used to determine if there's a rising edge. But because I also put the logic for detecting that in there as well, the detection itself has a one cycle delay, right? So it took one cycle for it to even detect the rising edge. Because you would think, like it should, you would think the d out would go high when instantly as din goes high. And you can do that, except I would have had to put the edge detection logic in a combinational always block, always com, or using an assign statement, right? Then I could have instantly detected that rising edge. But because the if statement for detecting the rising edge was also in a clocked, it gets delayed too, right? So there's a one cycle delay for it to detect the rising edge. Okay, here's another example from the same website. And by the way, there's a whole bunch of them. If you're interested in this stuff, it's a great website because you can test yourself on there too. And all of these, by the way, all of these modules are like less than 10 lines of code. They're all very simple, or at least all the ones I tried. Given a clocked sequence of unsigned values, output the second largest value seen so far in the sequence. If only one value is seen, then the output d out should equal 0. Note the repeated values are treated as separate candidates for being the second largest value. When the reset low signal reset n goes low, all previous values seen in the input statement should no longer be considered for the calculation of the second largest value, and the output d out should restart from 0 in the next cycle. So in this case, this is a 32-bit value coming in. And so, it's a stream of 32-bit cycles. So you can see here on din, I get H means hex, so 2, 6, 0, E, C, 0, 1, right? I guess these could be 4 bits, but it's actually, you can see the 32 bits here, but the values coming in are actually just 4-bit values. But anyway, you can see that after I get H6, then, I should say after I get 6, then 2 is the second highest value, so 2 gets spit out. And then after I get E, then 6 is the second highest value, and so on. So basically, it turns out this is pretty simple too. Oh, and again, there's a typo here. This had a parameter for the data width that I removed. I just replaced it with a constant. It should be 31 down to 0 here. Yeah. Yeah. So basically, there's the module line here, and then I have this thing called largest and second largest. And notice I initialize them here to H0. This is equivalent to having an initial statement. Remember I showed you the initial statement? So this is equivalent to initializing them with an initial statement. And then it just says always FF at pause edge clock. If the reset is asserted, then you clear largest and second largest. And then otherwise you just compare DN against largest and then second largest, and you use the priority ordering of this if then else statement to basically say if I find the largest, then put the previous largest into second largest and the current input into largest. Or if the current input is greater than second largest, just replace second largest, right? And then you basically just assign D out to be second largest, right? So as soon as second largest changes, it will instantly update D out because this is done in an assign statement as opposed to. Now, if I had put this in the always, then the D out would have it would update D out with an additional cycle of delay, just like in the last example. Okay, so those are just a couple examples of how you can build up, sequential logic. Now you can extend this to create memory arrays. A memory array or a RAM is like having an array of these flip-flops, or I should say an array of registers, but you can only access one of them for each address port that you put into the array. So in this case, if I create an array, say a 1024 by 32-bit array, this creates a 1024 deep array, 1024 entries, and each entry is 32 bits wide. So the ordering here is rows and columns, right? 1024 rows, 32 columns, 32 bits columns, right? Okay, just like in C and just like in linear algebra, rows come first, columns come second. Depth comes first, width comes second, okay? So this will create 32 kilobits in total, 32 times 1024. And if there's 1024 as the depth, then the address that goes in there is log base 2 of 1024, which is 10 bits. So I give it a 10-bit address, and that allows me to access just one at a time of these 1024 words. And every time I access one, I get all 32 bits out, the whole word, right? Okay. Okay, so I just said that. Okay, so how do you build a RAM in Verilog? Okay, this one is kind of tricky. So in many cases, so there's two ways that you can build a RAM like on an FPGA, or that you can, there's RAM on an FPGA, so really what you're doing is just writing a design that you want to utilize the actual RAM circuits on an FPGA. So on an FPGA, you have dedicated RAMs. If you want to use them, and you want to make sure that you use them and configure them in a certain way, a lot of times you'll use a tool called a IP generator, where you'll actually launch a separate program that then you tell it what size RAM you want, and it will generate a module for you, right? Another way to do it is just to write Verilog code that behaves like a RAM, and then hope that will map your code to a RAM. Does that make sense? Okay, so in other words, what I'm saying is that if you write it in a certain way, you'll use the desired thing on the FPGA that you want. Okay, so in this class, we're not going to generate the RAMs. We're going to use a specific coding style in Verilog and make it instance the type of RAM we want. Okay, so in this case, you'll see that there's a couple different components here. So the first thing you need is to declare the actual data in the RAM itself as a logic. So I say logic 31:0 mem 8191 down to 0. Now this is the weird syntax, because I just got done saying that the standard terminology for RAM is height by width, right? Number of entries by width. So 1024 by 32. That's how you would call, like if you were buying a RAM chip, you would buy it that way. It would actually be listed that way on the part, right? However, in Verilog, because I don't know why this decision was made, But notice it's reversed. So when you declare this thing, it says logic 31:0, mem 8191 to 0. The width is specified first, and the depth is specified next. And they're specified on either side of the name, mem. It doesn't matter. You don't have to call it mem. You can call it whatever you want. The point is you create a two-dimensional structure, a two-dimensional logic variable in Verilog, and you put the width first and the depth second, which is contrary to every other programming language I've ever seen, and contrary to like linear algebra. They always put the rows and columns, right? Okay, so keep that in mind. This is reversed for some reason. It's width then depth, just like with the test vectors. We talked about that last time with the test benches. Okay, then we have an address that is 13 bits in total because that's the log base 2 of 8192, so 8K. And then we have read data and write data. Okay, so this implies that we're going to be able to read and write to this memory. So by the way, the one I showed earlier, this one was also read and write. Notice the data in this case is bidirectional. So I was about to say that one is only read, but that one is also read-write. Okay, so then we have a write enable and a clock. Okay, so let me skip the initial for a minute and go down to this part. So down here I have an assign statement and an always underscore FF. So the assign basically takes the memory at address and spits it out onto read data. But this happens outside of a clocked statement. This isn't clocked, this is an assign statement, which means that this read is an asynchronous read, meaning that anytime the address changes, it will activate this assign and immediately update the read data, right? Then the always underscore FF is clocked, and it has an enable called write enable. And so if you get a rising edge and the write enable is asserted, then it will update mem at address with write data, right? So in other words, this will always read whether I want to read or not. It will always be reading from the memory with the address input, but it will only write if I assert write enable and wait for a clock edge to make it actually write. So it has a synchronous write and an asynchronous read. Does that make sense? Okay, and then there's also an initial block that initializes the memory with this. Again, this is kind of an arbitrary syntax, but read memh, mem.txt, mem. So this takes the file mem.txt, which is just a text file with hex values in it, one on each line, or I think you can even put any kind of white space in between them. It's kind of flexible in that sense. And then it initializes mem. Yes?
In this example, it's like the previous one. It was asynchronous read and synchronous write, but we can change that behavior based on...
Right, yeah, you can change it in the code here. Now all you have to do to make it a synchronous read is to basically move this read data inside the clocked block and take a sign off and change it to a less than equal non-blocking assignment, right? Okay, now here's the weird thing about this though. If you put this on an FPGA, it's not going to use the RAMs on the FPGA. It will fail to map this to the RAMs because the RAMs on the FPGA all have synchronous reads, just because that's how they work fundamentally, the circuits work. So if you put this on an FPGA, it will still work, but what it'll end up doing is instead of using a RAM, it will actually create an array of registers, and it'll use a multiplexer to select one for reading. And it'll use a decoder for selecting one to write, okay? So this actually turns out to be very inefficient because there's a lot more RAM bits on the FPGA than there are flip-flops. And again, registers and flip-flops are the same thing, right? Flip-flop bits, right? So, but if you have to have an asynchronous read, then you don't have a choice. You're just going to have to go with that, right? All right. Okay, so here is an example where I've moved the read data now down into the clocked code, and this makes a synchronous read, right? Which means that if I want to read, I got to wait a cycle. It's going to take a whole cycle to read. I get an address, put an address in there, I send my address in, and the next cycle to read. Okay, so this is a little difficult to read, but tried to show this actually in ModelSim. So what's happening here is I've got the data in the RAM is initialized to be the same as the address. So if I read from address 4, I'm going to get data is going to be 4, right? If I read from 5, I'm going to get 5. So basically I've just stored the address into each slot on the RAM, right? So you can see that as soon as I change the address to 5, I get 5, meaning because this is an asynchronous read, right? Now down here, if I put 5 on the address, notice the 5 doesn't pop up until one cycle into the future, right? So in other words, you can see that the address here is 456, and I get 456 right under the address. But here I've got 4, 5, and 6, and the 4, 5, and 6 are there, but they're lagging by one cycle, right? There's a lag. There's a one cycle lag between when I request the data and when I get it, okay? Now, one thing you might ask is, oh, wait a second, can I create an asynchronous write? Do I have to put the write in a clocked block? Yes, there is no RAM technology that will do an asynchronous, at least not that I've heard of. It might be something obscure. But RAMs always require a clock to write. But you can optionally, but it's optional for read if you want an asynchronous read. But like I said, most RAM circuits require synchronous reads. Okay, and then finally, let's see. So here, it's a little subtle, but there's this write enable. The write enable is high here, and so basically I'm writing to address 6, and the data I'm writing is dead beef. And you'll notice that I write dead beef here. After I write it, it shows up because I'm reading. So basically, I keep address 6 on the address bus. So I set 6 on the address. So initially, I get 6, which is the initial contents of that address. But because I'm writing dead beef, the dead beef shows up one cycle later. You see that? So basically, I read this is the original value of 6, this is the new value of 6, but it took one cycle to write. You can see that the writes are synchronous because even though I put the dead beef in here, it doesn't show up on there until the next cycle. However, down on this one, the dead beef actually takes a cycle to write and then another cycle to read, which is why the dead beef is way over here 2 cycles later over here, because I wrote dead beef, it took a cycle to reflect the write and then another cycle for the read of that thing to get out. So there was a 2-cycle delay for dead beef on here because this, again, synchronous read and write versus on the top it was synchronous write but asynchronous read. Okay, so that all leads us to the register file that we want to use for the class project. So we're going to give you the register file inside the project skeleton for lab 3, just because you can use it, just so you don't have to build it yourself. It's not actually the same as this one, though. The one that we have in the skeleton is the one that one of my TAs wrote. This is the one I wrote. I probably should put, I mean, they're both equivalent. So in this case, this is the symbol on the right. So the register file requires, and this is kind of a challenge. RISC is a 3-address architecture, which means the instructions have 2 operands, 2 inputs, and 1 output register, right? 2 input registers, 1 output register. And you want to pipeline it, which means ideally you're trying to execute each instruction in one cycle, right? In steady state. You should be able to ideally, the number of cycles per instruction should be 1 in this case, right? Or at least 1, and like, if not more, if you can get more, right? What that means is that the register file, even though it looks like a RAM, meaning that it has an address, it has addressable memory, it has to have 3 ports to match the 3-address architecture. We have to be able to read the 2 operands and write a result all at one time. And again, the RAMs on the FPGA only have up to 2 ports, not 3 ports. This would be a 3-ported RAM, right? No FPGA has 3-ported RAM. I've never seen that before. So you can do it, but you're not really creating a RAM. You're not using one of the RAM circuits on the FPGA. You end up just creating an array of registers with muxes and decoders to handle the addressing logic, right? But that addressing logic is put in there for you, commensurate with the way that you write the code. So the code is structured to have 3 ports, and the read ports are asynchronous reads in addition to that. So this is, by the way, if you've ever wondered why, you might have wondered, like, there's only 32 registers, right, on modern CPUs? Like, you know, MIPS and ARM. There's only 32 registers. And there was 32 registers 40 years ago. Why isn't there been no advancements? There's been no growth in the register file, right, in all this time. It's because register files have to be small for this reason. They have to have a lot of ports, right? And that's the reason why they have to be kept small, because ports are expensive. Because every port requires decoding logic and multiplexing logic. So, but anyway, so this one has these, basically, there's 2 read addresses, and then there's a write address. So there's 3 addresses, and these are going to be connected directly to the fields on your instructions. So your instructions are going to have address fields. You're just going to create connections directly from the instruction fields directly into these ports. Okay, and then there's a write enable, a clock, and then there's a read data 1 and read data 2. So if you write a register, you don't get any kind of response from this guy. You just give it an address you want to write to, the data you want to write, and you do write enable and clock it, and you write. And there's no kind of acknowledgement or anything. You just have to assume that that change was made internally, right, to the register file. If you read, on the other hand, you just give it 2 read addresses, and it'll spit out the corresponding contents of those addresses in the register file. And it's going to read in every cycle whether you want to or not. So even if you don't need 2 registers to be read, you would just ignore the output of the corresponding outputs on the register file. Okay? So notice here that sorry, I keep thinking I can point to that. Notice that we declare the memory here, logic 31 to 0, mem 31 to 0. This creates a 32 by 32 register RAM, which is 1,024 bits in total, 32 times 32. Then the read datas are put in here as assigned statements. I think the one that we give you in the project skeleton actually puts these in a combinational always block, because the TA that wrote that preferred that style. And then there's an always underscore FF that handles the write logic, right? So even though there's just one memory, the behavior is being deployed in 2 assigned statements and an always block, right? But they all reference this mem, right? Now you'll notice a few things that are weird here, though. What's going on with these read addresses? Well, I put a check in. I use a ternary statement here to check to see if read address 1 is 0. If it's 0, then I want to spit out 0 on the corresponding read data, because in MIPS and in RISC-V and in MIPS, register 0, if you read register 0, you always get 0 as the contents of register 0. And I have that logic on both of these read ports. If the address is not 0, then there's this other condition that might happen where if I read and write the same register at the same time, I should get the value that I'm writing to it. Why? Well, if you go back to this example, check this out. You can see this happening here. This top waveform is an asynchronous read, and I'm writing dead beef on on address 6. Now, notice here that in this case, I only have one address port. The read address and the write address are the same address. In the register file, I have 2 separate addresses for that, right? But the principle is the same. I have 6. I'm writing to 6. Address is 6. Write enable is 1. You can see write enable, the rising edge for that is right here. The write data is dead beef, right? However, the dead beef doesn't come out until the next cycle, right? So I'm reading the old value of address 6, which is the value 6, right? The updated value, which is dead beef, is not going to come out until the next cycle. Why? Because it takes a cycle to write. The writes are synchronous. It takes me a cycle to write. But in MIPS, in MIPS and RISC-V, you have this possibility of having to read and write the same register at the same time. And because it's pipelined, and I'll get to the pipelining here in a minute, but the read and the write are actually coming from 2 different instructions. The write could be coming from instruction n, and the read might be coming from instruction n plus 1. You know, so in other words, I want to, whenever I do a read and write at the same time, I need to enforce the ability to get the new value that I'm currently writing. This is called a bypass. So what this ternary statement is doing is it's saying if read address 1 is equal to write address and write enable is asserted, then I'm going to not read the memory, I'm going to bypass the memory, and instead I'm going to use a mux to forward the data that I'm writing and spit that out as if that was what's in the RAM, even though it's not in the RAM because it would take a whole cycle to write that, right? So this is called a bypass here. This is a bypass condition. Because otherwise, if you read and write at the same time, you're not going to be immediately getting the new value you're writing, right? There'll be a cycle delay because it takes one cycle to write. That's just a property of RAMs. It takes a cycle to write a RAM. And otherwise, I just read what's in the memory. Okay? And then likewise down here, this takes care of writing. Now, some people, and I think even the register file design that we give you in the skeleton actually has something in here in the write logic that says that if you write to register 0, don't do it, right? But you don't need that. According to this design, if you write to register 0, it will actually write to register 0 in the RAM, but you'll never be able to read it because the read logic prevents you from ever accessing that array, that value, right? So the philosophy here is if someone writes to register 0, let them write to it, but it just goes into a black hole. It can never be read again, even though it physically goes into the RAM. Okay, so that's now there's another piece we're going to give you too, which is the ALU. This also is in the project skeleton. The ALU is a little simpler. You'll notice there's no clock on the ALU. It's a combinational logic circuit. It takes A and B as the inputs, 32 bits each, along with a 4-bit opcode, and it produces a 32-bit result and a flag, a single-bit flag called 0. This ALU is capable of performing, I think 13 different operations. Now there's 16 values of the opcode, obviously, because it's 4 bits, but 3 of those enumerations of opcode are redundant. They map to the same operation. So you'll notice, like for example here, if the opcode is 1100, 1101, I'm sorry, no, 110, 1101, 1110, or 1111, they all do the same thing, A less than B. It's a comparison, right? Unsigned less than operation, right? So basically, A and B are just going to be connected directly to your register file. So if the register file has this read data 1, read data 2, right? Essentially, those are going to be connected directly into A and B on here, although there's an exception. If you do an immediate instruction, there's going to be a mux that can forward in an immediate onto B instead of the read data 2. But basically, the intent here is for, like if you're doing an R-type instruction, a regular register type instruction, the register file will feed directly into this ALU, right? And then the opcode is going to be driven by the control unit, which I mentioned earlier is that big if-then-else statement, essentially, that sets the control signals. So the op is a control signal that's going to be driven by the control unit. And then R is the result. What's that going to go to? Well, basically to the write data on the register file, right? But it has to go through a pipeline register first because of the pipelining. But essentially, the R is going to go, usually is going to be routed back to the register file for writing. So you can update the result register. And then the 0 is a flag that's going to be used. It's just going to be asserted whenever R is 0. And that's going to be used as our branch resolution logic. So that's going to go back to the control unit and tell the control unit whether we should take the branch or not. That's going to be basically an indicator of equality between A and B. Because whenever we do a branch, we're going to subtract. And if you subtract A and B and the result is 0, that means they're equal and they should take the branch, assuming branch if equal. Okay? Make sense? Okay, now we had to put some weird stuff in here. We have A, OR, XOR. These are basically bitwise logical operation. We have add and subtract. But then there's 3 different multiplies. Multiply low, multiply high sign, multiply high unsigned. You guys know, I'm sure you guys all know exactly what that's for now, right? After having done lab 1, you know that there's 3 multiply instructions in RISC-V. Those 3 operations just map to those, right? Mul, mul-hu, and mul-h. And then there's shift left, shift right, shift right arithmetic and another shift right arithmetic, right? So these are redundant. So I guess there's what, 12 unique operations, not 13, because we've got, oh no, there is 13, yeah, because there's 2 redundants here and 1 redundant here. Yeah, there's 13 unique operations, yeah. And then we have comparisons. These comparisons are used for the set less than operation instruction, as well as for branch resolution. Everyone with me? Okay, so this is the code for the ALU. Now this one is actually the code that we give you. So we've got module ALU. There's some intermediate signals here. There's some weirdness here, and this is why we give you the code. This part is, so in Verilog we use this logic type, right? Which is unsigned. It's an unsigned type, but you can actually treat it like signed with $signed. It's a Verilog function, which we use for the signed multiply, right? So it's a little hacky, but that's how you have to do it. And then the shift. So maybe one of you guys might figure this one out, but Verilog has shift operators in it, right? You can just say less than, right? But for whatever reason, we couldn't get those to work. So we had to create our own shifter. So this shifter uses, and this is a kind of a cool use of an always com, but basically you have always com, you take A and put it in the shifted. And then you use the curly brace, curly brace bit twiddling thing to basically shift it by either 1 bit, 2 bit, 4 bit, 8 bit, or 16 bits, or any combination thereof, using blocking assignment statements in order to be able to shift by any arbitrary 5-bit shift amount. So for example, if I want to shift by 5, what I do is 5 is 1, 0, 1 in binary. So I shift it by 4 bits to the left, and then I shift it again 1 bit to the left, right? And in total that gives me 5, right? So this is a logarithmic shifter, basically, and it's taking advantage of you notice the equal sign here is not just a standard equal, and that's very important because this is a staged operation, and so this code has to honor the dependencies, the data dependencies in here, right? But you don't have to worry too much about that because you can just use this. But I can't remember exactly what the issue was with the Verilog shift operators, but we couldn't get those to work. And then finally, we have this big ternary operator that just simply selects one of the operations based on the opcode. So this just creates a big multiplexer. And this, I'm sure this is not the most efficient way to do this, because you'll notice that we do the multiply, for instance, I think we're doing a signed and unsigned multiply at the same time. So this will create like 2 multipliers, as opposed to reusing the same multiply hardware for signed and unsigned. Again, this is probably not the most efficient way to do this, but it works, and this is one we've been using for the last few years. Okay, so in Lab 3, the goal is to build a RISC-V processor from essentially scratch, although we are giving you the register file and the ALU. We want to create initially a processor that can execute 22 RISC-V instructions, which is actually, RISC-V doesn't have that many instructions in the core instruction set. So we're trying to create the core instruction set and including the multiplier extensions, right? Now you'll notice from this list, basically most of these instructions are number crunching instructions. So add, subtract, multiply, set less than, and, or, XOR, shift left logical, shift right logical, shift right arithmetic, load upper immediate, and CSRRW. So aside from CSRRW and load upper immediate, right, these are just number crunching instructions, very simple. There's no branch or jump instructions in here, which means that any code you write for this processor can't have any conditional execution whatsoever, right? You can have loops, but the loops have to be unrolled, meaning that you take the body of the loop and you have to like copy and paste it for as many iterations the loop has. And of course, you'd have to have a static number of iterations, constant number of iterations. You can't have a variable number of iterations if you do that. If there's a constant number of iterations of the loop, you can unroll the loop and make a loop, assuming you have enough space in your instruction memory, right? But you can't do if statements here. In the next lab, we're going to add the branch and jump so we can do if statements, right? Now, what's the LUI? I think I explained that one. The LUI instruction is used for initializing the upper bits of a register, right? And the CSRW instruction stands for, I think, control status register read write. And we're going to use this for I/O. This is going to be our mechanism for performing I/O. Okay, so in order to do this, we have to implement 3 instruction types. There's the R type, I type, and U type. Now, you guys probably remember, you might remember, do you remember from 212, the instruction types in coding? So remember with MIPS, they only had 3 types, R, I, and J, right? And for integer, their floating point formats were separate. But for the integer instructions in MIPS, there was only 3 encoding formats. The RISC-V guys, the guys that came up with RISC-V, decided that limiting to 3 encoding formats is a dumb idea. And they just went crazy with the instruction formats. There's like 20 different instruction encoding formats in RISC-V. They did not constrain themselves. I think when they look back retrospectively and they said, trying to fit everything into 3 encoding formats in MIPS was a bad idea. There was no reason to do that. So RISC-V has lots of instruction encoding formats. In this lab, we only have to worry about 3, but there's a lot more. And the U type is literally only for the LUI instruction. It's the only instruction that uses that type. So they have a whole encoding format for one type. Now, you remember from MIPS, they had the I type covered all the branch instructions, right? And all the immediate arithmetic instructions, right? But they don't, in RISC-V, they don't try to reuse these encoding formats. So we have R type, I type, and U type. R type is going to be, I listed, I don't know how well you can read that, but basically of all the instructions, of the 22 instructions that we're going to build, all the ones that are R type are listed there. I put them all there. I type, all those instructions are here. You'll notice the CSRW instruction is an I type. And the U type, like as I mentioned, only has 1 instruction that uses that, the load upper immediate. The other thing that's a little weird is the encoding formats almost make no sense. So you'll notice there's an opcode which is 7 bits. Remember in MIPS it was a 6-bit opcode. And remember that the R types had a function code that was 6 bits. Here we've got 10 bits of function code, and they're in 2 different spots. You've got a func7 field and a func3 field and an opcode field. You have to use all 3 of these fields together to figure out what the instruction is, and they're all in different spots. So because of this, I have never actually memorized. I used to have the MIPS encoding formats memorized. I could tell you exactly what bits were each field. I never memorized this. This gets kind of wacky. I always have to look it up. And also notice the opcode is in the lower bits. Remember in MIPS, it was the first 6 bits. It was in the upper bits. So this is all messed up compared to MIPS. But the registers are RS1, RS2, and RD. And RD field is always 11 down to 7. So if any instruction writes a register, it's always in bits 11 down to 7, which simplifies this a lot because you can then take these bits and shove them directly into the write address of your register file. That wasn't the case in MIPS. MIPS had different destination fields depending on the instruction, right? So this simplifies things a bit. Likewise, RS1 and RS2 are always in the same spot. So in the I type, there is no RS2, but there is an RS1, and it's in bits 19 down to 15, so they're more consistent. You'll notice the I type has only a 12-bit immediate, unlike the 16-bit immediate of MIPS, which is, I don't know why they did that. But the U type has a 20-bit immediate, which is meant to complement that 12-bit, because 20 plus 12 is 32, right? So between this 12-bit and this 20-bit, you can initialize all the bits in a register, but it's going to take 2 instructions to do it. An LUI followed by like an OR-I, okay? Any questions about that? Okay. Okay, so how about the CSRW instruction? Okay, so this one is a little strange. the problem this is solving is that we want your CPU to have I/O, even the early version of your CPU. Now, how do you normally do I/O with a CPU? Normally you use load and store instructions. You load and store into I/O address ranges, right? But we wanted to give you this capability to do I/O before we do loads and stores, right? In fact, we don't even, last few semesters, we'd never even added loads and stores to this. We didn't even add a data memory, right? So these instructions normally are meant for status and flag registers in RISC-V, but we're going to subvert it a little bit and use these for I/O. So if you download RARs from Blackboard, that version has been modified to include 4 control status registers, of which we only use 2. One for the keys is an input and one for the switches. Sorry, that's wrong. One for the switches, which is an input, and one for the hex displays, which is an output. And you guys will reuse the 7-segment decoders. You guys with me? Okay, so now the problem is that if you read the instruction set architecture, the way these work is if you do a CSRW, it takes the control and status register, which is the second thing in the instruction here, which is stored in the 12-bit immediate field, which means this control status register is 12 bits, which is 3 hex characters, 3 hex digits, 12 bits, which means you have 4,096 control and status registers available in RISC-V. And that's the second thing you put here. The way the instruction is supposed to work is it's supposed to take whatever was in that status register and replace it with whatever's in the RS1 register, right? But then it also takes whatever was in the status register and put it in the RD register. In other words, what it does is an atomic swap, basically. It swaps, it moves the RS1 into the CSR, and whatever was in the CSR, it puts in the RD at the same time, right? So it's a simultaneous exchange, right? You put stuff in, you get the old stuff out atomically, right? However, in this class, that doesn't make any sense because we can't read the hex displays because they're an output, right? Likewise, we can't write the switches. That'd be cool if we could, though. It'd be cool if there's actuators on there and you could actually have the FPGA flip the switches itself. But it can't do that, right? There's no actuators on there. It takes a human to flip them. So in this class, if you use the CSRW instruction on the hex displays, it's treated strictly as an output. And if you use them on the switches, it just uses an input, right? So it's a little bit violative of the RISC-V instruction set architecture semantics, but it's just how we had to hack this a bit. And likewise, the actual numbers here are F00 is the switches. So if you CSRW F00, it puts the switches into RD, and it ignores the RS register there, RS1. And if you access F02, it takes whatever was in X1 and puts those in the hex displays, and in this case ignores X0, right? Make sense? In our RARS code, our version of RARS on Blackboard actually has these special registers built in. If you download the vanilla version of RARS, then it will actually give you an error if you put these instructions in. It'll give you a runtime error. Okay. Okay, so the goal of this lab is to create a CPU and an instruction memory, which is on chip. It's treated as a ROM because we're going to initialize the instruction memory when you program the FPGA, and you can't write to it. So it's basically just a ROM. Now, just for the record, we used to have, in an earlier version of this class, we use these in-system, they have these things called in-system memory content editor in the FPGAs, where you can actually use a JTAG-based method to load these instruction memory after the fact. After you program the FPGA, you could load in place. That's possible. But no one ever used it because anytime people wanted to debug their code, they would just reprogram the FPGA anyway, so it became pointless. So we took that out. So now if you want to change your software, you have to also reprogram the hardware too with it, right? So like I said, it's basically treated as a ROM, read-only memory. So it's 32 bits wide, and we make it 4,096 entries deep. But you can actually change that. If you guys don't want, if you want to make a bigger instruction memory, you're more than welcome to, but it's already way more than we need, even at 4096. And then we'll have your hex decoders in here. So the CPU, the instruction memory, and the hex decoders will all be on chip. The inputs will be the clock 50, key 0, which is your reset button. Yeah, it's literally a button. Key 0 is a button. You hit the reset, like your reboot button. The switches is an input. And then the output is going to be your 56 bits of 7-segment hex displays, right? And they're all in parallel. As I mentioned in lab, a lot of times when you have 7-segment displays, they're multiplexed. You know, they're kind of, you have 7 bits and they keep time sharing. So if you film a 7-segment display with your phone camera, it looks like it's flickering, right? Whereas on these boards, we have all 56 bits go straight out, so there's no flickering. It's actually, you know, it's actually lighting up those things consistently. So those all 56 bits will come out. Now, by the way, this is not meant to represent the way your modules are represented. This is a functional diagram. This is not, your modules are not going to be organized this way. Okay, so how to get started. Everyone always has trouble getting started with this lab. So we gave you, this is the starting point. And this might not be, some of you might think this is not good design practice. But I tried to simplify this so I could show it in a slide. So you need a module called CPU. You'll have a clock input and a reset input. And you also eventually need the switches coming in and the hex display output. But I don't have those. That's like a GPIO. I don't have those listed yet. So right now, there's just a clock and a reset input. Notice the reset is active low because the buttons are active. A lot of people make this mistake. The buttons on the board are active low. So when you push the button, it gives a 0. When you release it, it gives a 1. So keep in mind that if you tie the button directly to your reset, it should be an active low reset, which is why I put reset_n here. So I instance the instruction RAM, which is kind of a misnomer because, like I said, it's really a ROM, but I call it instruction RAM. Notice again, the width is first and the depth is second. The initial statement is program, it loads in program.rom. And then I have something called PC_fetch, which I initialize to 0. And I have something called instruction_ex. Okay. Now these are named deliberately. The reason there's an _fetch on the PC and an _ex on the instruction is because this PC is operating in the fetch stage. The instruction is in the instruction stage because this is pipelined. Then I have the basically the fetch logic here. So always at FF, always FF pause edge clock. If I'm resetting, reset the PC fetch in the instruction EX. And by the way, notice that is I have that as a synchronous reset, and remember, I just found out like a week ago that it's actually better to make that asynchronous, right? So there should technically be pause edge clock, pause edge reset there, right? Or I should say probably neg edge reset, right? Because it's active low. And then otherwise, this thing will increment the fetch. PC fetch gets incremented by 1 every cycle because there's no jump in branch instructions, so the PC fetch will always be endlessly incrementing. And instruction EX is going to be reading the instruction RAM at PC fetch, right? So this is your starting point. This will actually allow you to load a program and have it spit out a stream of instructions from that program 1 every cycle, right? Now, obviously, it's going to go through all 4096 instructions and then loop back to the first one. If your program isn't 4096 instructions long, then once it gets past the end of the program, it's going to be putting zeros out, which in RISC-V, zeros are no-op instructions. They don't do anything. So that's okay, right? And this will automatically create a loop a natural loop because it'll keep rolling back to 0, right? So it'll keep executing your program repeatedly, right? Okay.
PC by 32-bit.
Oh yes, good question. Thank you. Yes, yeah, great question. Sorry. Yeah, the instruction memory, normally you'd increment it by 4 because normally memory is byte addressed. And if the instructions are 32 bits, you'd have to increment it by 4 bytes. But in this class, we always make the instruction memory word addressed. So it's a 4096 by 32 memory, which means that every word is 32 bits. So if you increment the PC by 1, you're actually getting a different block of 32 bits out. So you don't have to increment it by 4. Okay, so you just have to increment it by 1 in this case. Okay, so now another tip here. So you guys know about SymTop, right? So SymTop you had in lab 2. SymTop was meant to be your top level for your testing environment. This is what's simulated when you type CSCE 611 SH test bench. It's also useful for running standalone in QuestaSim. I don't know how many of you guys have been doing that. You might have not done that yet on lab 2. You might have done all your testing in just plain test bench or running on the FPGA. You're probably going to have to go into QuestaSim though for debugging this lab, just to let you know, because this lab is a big jump in difficulty compared to the last one. And it's just, it's that way because we haven't been able to figure out a more natural step, right? We tried, at one point we had everyone just make the fetch stage by itself, but that was really confusing. Building a fetch stage without the rest of the CPU is like really confusing for testing. It makes more sense for testing if you have a fully functional CPU, even if it's just a few instructions, if it supports few instructions. Okay, so yeah, so SymTop is SymTop. This is just like before. Top is your top. Now top is for the FPGA, top level design, and it has the special pins. All the inputs and outputs are your special pins, and we give you that one. When I say special, I mean the ones that map to actual FPGA pins and the mappings. And then CPU.SV will go inside there. Your 7-segment decoders, though, will be in top, which they already are, right? So you guys I think you already have them in there, so you just leave them there. Of course, you're going to break the connection, though, between the switches and the decoders, because the switches will now go in the CPU, and the CPU will drive the decoders. In 212, you should have learned that there are 5 stages of instruction execution, or at least in the way that it's presented in that textbook, in the Hennessy and Patterson textbook. So you begin with fetching an instruction from RAM, and then you decode it, which means that you convert its control bits to control signals, right? And you also read the source registers, the register operands from the register file. And then you execute, which is the ALU operation. That would be, add, subtract, multiply, divide, shift, bitwise logical comparison, whatever. Then there's a memory stage where you access memory. You perform a load or store operation in memory. And then there's a write back. In this class, we're not going to implement the memory stage because we're not going to implement load and store instructions. So there's really just 4 stages. And also, if you have trying to think now, see if I remember this correctly. If you have enough stages in your pipeline, you have to be able to support forwarding, which is where if you have an instruction that writes a register followed by an instruction that reads that register, if the distance between those two, if the distance between the writing of the register and the reading of the register is more than 1 cycle, then you have to implement forwarding. In other words, that bypass in the register file isn't enough. It's not enough to do the job. You still will have to forward because it may be too late to forward, in other words. So all that's to say that we're simplifying this to make it a little easier on you guys into a 3-stage pipeline. So the first stage is fetch, the second stage is decode and execute together, and the third stage is write back. So ideally, you'll have 3 instructions being executed at the same time. One's going to be in write back, then the one that appears after that in the code will be in the execute, and the one that appears after that in the code will be in the fetch. Does it make sense? So you have this pipeline. And so, right, so it'll look like this. So like, for example, here, if we have these 3 instructions and they're color-coded, gray is the earliest instruction, and then teal is the second earliest, and purple is the third the last instruction in the sequence. Then the earliest instruction is going to be in write back, while the second instruction is in the middle stage, the execute stage, and the first instruction will be in fetch, right? Now, this allows you to have a 1-stage difference between the write back, like when the register is written to the register file, and when it's read from the register file, right? Which means that if you have a data dependency in your code where you write and then subsequently read, you can handle that in the forwarding pass that I talked about in the register file. The register file has a bypass that says if you read and write at the same time, it's okay, no problemo, right? And that's possible only because worst case scenario, I'm writing back while I'm reading that same register in the next cycle, right? You guys with me? Okay, now if I split decode from execute, that's no longer the case. Then I may have an instruction in execute with an out-of-date register and another instruction that came before it in write back with an up-to-date version of that register, and there would be no way to bypass it through the register file. You'd have to implement a separate forwarding pass to send that result back. And that complicates the design, so we're not going to have to do that with a 3-stage. You guys with me? Okay, so 3 stages, there's 3 instructions at a time. So this gets a little confusing because as you simulate your design in Questa Sim, which you're probably going to have to do in this lab. You might not have had to do that in lab 2, but in lab 3, if there's any bugs at all in your hardware, the only way to address those bugs is through debugging through Questa Sim in your waveform. At least that's the only way I know. Right, I guess if your first design works, then you don't need to do that, but that's never the case for me. Okay, so as you look at your signals though, you're going to have signals that relate to the instruction in fetch. You're going to have signals that relate to the instruction in execute, and you'll have signals that relate to whatever instructions in write back. Right, so in order to differentiate them, I have proposed this scheme where you put a suffix after your signals to designate which instruction those signals are dealing with, right? So PC_fetch is the program counter. That is the address of the instruction being fetched. It is not the address of the instruction being executed because that would be one earlier, right? That would have a program counter that's one earlier. You guys with me? Right? And likewise, there's an underscore write back deals with the instruction that's in write back. So this is my original idea that I'm very proud of, is putting these suffixes at the end of it. It makes it debugging much easier, right? Of course, you don't have to do that. It's up to you how you name these signals. This is my suggestion. So PC fetch is just basically the output of the program counter, which is just a counter. Now, I've showed you guys how to build a counter before. It's pretty much just always at POSIX clock, PC equals PC plus 1. That's like one line of code, very simple. That's really all that is, right? Now, the way I'm showing it here, though, looks a little bit more complex because, well, first of all, I violated the rule where data should, in a block diagram, data should flow from left to right, right? Input should be on the left, output should be on the right. But you can see in this case, because there's this weird arrangement where, well, I guess I could have maybe I should have put the program counter over here on the left. But anyway, what's happening here is that I've got the program counter. I'm adding 1 to it and then feeding it into the address on the instruction memory, which is a ROM. So it's a ROM, meaning that the address goes in and it's a synchronous read, which means in the next cycle, the instruction comes out, which means the output of that ROM is called instruction_EX, which is the actual instruction that's in the EX stage, which means it was the instruction that was fetched in the previous cycle, right? So what'll happen is if you look at PC fetch, it might say 10, right? But then the instruction EX is going to be the instruction that's at address 9, right? Because I would have fetched 9 in the previous cycle. So if this is 10, then this guy is going to be the instruction at 9, right? Because this instruction EX is going to lag behind the program counter because it takes a cycle to fetch because it's a synchronous memory. Does that make sense? So you're going to see that, again, if you look at your code, you're going to see this guy is lagged behind this guy. You're not going to have, this PC fetch is not going to be the address of the instruction coming out. Okay? Now, one of the things that one of my prior TAs suggested was this encoding. I mentioned on Monday that the RISC-V instruction encoding is bonkers. It's like they have Func3. What's that all about? Why is there a Func3 and a Func7? And I don't understand any of that stuff. And I don't even have it memorized, right? I couldn't tell you which bits are Func3. I don't know, right? So a former TA came up with this idea that I thought was pretty good. You can create a module or even just a set of assigns. It doesn't have to be an outlined module. It can be inlined if you want. But basically, you can rename a signal very easily. If you have two logics, A and B, and you just say assign B equals A, then B and A are the same thing, just two different names, right? You've renamed it. So you'll have a signal called A, and whenever that changes, it'll activate the assign statement and update B accordingly, right? So you can use that trick to actually create named logic variables for each of the fields in the instruction. He called it a decoder, which it's a little confusing, but I still went with that name. But basically, the instruction EX comes in, and you can extract each of the, I guess there's 9? Yeah, there's 9 fields in the instruction, some of which overlap one another because there's different instruction encoding formats, right? So for example, you have an immediate 12, right, which is, I think, the upper 12 bits of the instruction. If it's an R-type, R-type? Oh, I already forget. Is it R-type? I-type, right, sorry, I-type. If it's an I-type instruction, the upper 12 bits is called immediate 12. But if it's a U-type instruction, the upper 20 bits are called immediate 20, right? So technically, these two fields overlap one another, in 12 bits, but that's okay. You can still have two separate signals called immediate 12 and immediate 20. And obviously, only immediate 20 is relevant. Immediate 20 is only relevant if it's a U-type instruction is in the execute stage, right? That's been fetched, right? So you can basically just rename these. This will make it a lot easier to debug because otherwise, when you're debugging your code, you're going to have to manually figure out what's inside the instruction. Because remember, the instruction's in hex or binary, right? It's machine code. So you're like, well, what instruction is this? I don't know. What's the destination of the, I don't know. And keep in mind that in hexadecimal, the hexadecimal digits are grouped by groups of 4 bits each, right? But the fields in the instruction are not on the 4-bit boundaries, right? They're not, so in other words, you can't look at the hex digits and figure out what register you're writing to based on the hex because the registers are 5 bits and they don't fall nicely on the boundaries of 4-bit groups. So looking at the hex is useless. You'd have to look at it in binary, and then you'd have to find which fields the register destination is, and then you'd have to then interpret that binary value as a decimal. So it's much easier if you just put this little thing in here that renames them. Does that make sense? So I'm just talking about a bunch of assign statements, basically, right? And declaring some variables. Okay, let me go back here to fetch. Okay, so the fetch stage is very trivial. I actually gave you the code for that on a previous slide. The fetch stage consists of the instruction memory and the program counter, and basically a program counter that can increment itself every cycle, right? And the program counter just increments itself continuously, right? There's no branch and jump instructions, so it never deviates from its path of being incremented by 1. Eventually, it'll get to the maximum PC value, and then it'll roll like an odometer back to 0, and it will create this natural loop that'll keep executing your program over and over again, right? Because we're using an FPGA, and all the memories are configured by the bit stream, that means that any unused instruction slots in your instruction memory will be 0, which are interpreted as no ops. They'll just be ignored, basically. So in all 0, actually does map to an instruction, but it's mapping to an instruction that writes to register 0, which has no effect on the state of your CPU. So it's basically a no op, okay? All right, so that's all that fetch is. So pretty much the only signal that will have the underscore fetch suffix is going to be the program counter, so that's nice and easy. Most of your signals are going to be dealing with the instruction being executed. So most of your signals will have an underscore EX. So you have function instruction underscore EX, and then you have the different fields of that, which I'm showing here, going into the control unit, all of the control fields. And there are 4 of those. There's the opcode, the func3, the func7, and the immediate field, which is used as a control information for your CSRW instruction. That's the control register. So that technically counts, at least for this class, as control information, okay? Okay, so then, oh yeah, one other thing. The write back, there is a write back stage, and like the fetch stage, the write back stage is very simple. It consists just of the write port on the register file, right? So that's going to be your write address and your write data, both of which just have to have a register to delay them to push them into the next cycle. So very simple. So you should only have three, not two, but there's 3 signals that have the _WB suffix. The write enable on the register file, the write address, and the write data, right? Those are the only 3 things that are in your write back stage. Now, some of the students in this class look at this 3-stage pipeline and they say, you know, we really should have a module for each stage. We should create a separate module for each of the 3 stages, which you're welcome to do. I don't do it that way because the problem is that the register file is in 2 different stages. It's in the execute and the write back, right? So where do you put the register file, right? It's kind of confusing. Also, as you outline code in Verilog, by outline I mean you take some code and you put it in its own module and then you just include that module somewhere. That's called outlining. When you outline code, you have to connect all the wires that would have, you know, traversed the boundary between the code that you're outlining, right? And it could get a little tedious, let's say, to connect all the ports. But I'm not trying to tell you not to do that. It's better design practice to actually have, you know, relatively small modules. I had a student, Charles, who, you know, he never wrote a function or a module that was more than 24 lines of code. He said that only a newbie would do that. Like you know, everything should be 24 lines or less. If not, outline it into a function, right? Because he was a programming purist, right? So, but see, the way I do this is I put the whole CPU in one module, right? I mean, aside from the, like, obviously the register file and the ALU, which are separate modules that we provide, you have to instance those. A lot of students in this class will put the control unit in a separate module. I don't even do that. I just inline that too, right? And I'll talk more about that in a minute. So does that make sense how that works? So this thing here is a register. So the goal of this lab, in a nutshell, is to basically translate these pictures to code, right? That's essentially what we're asking you to do. Because the pictures represent the schematic, the structure of the CPU, and your goal as someone learning SystemVerilog is to understand how you translate schematics into code, right? So we've provided the pictures, and the goal is to essentially write the Verilog. So we've already given you the design in a sense. Now, by the way, this is not a great design either, because by choosing to make it a 3-stage pipeline, we've doomed ourselves with regard to clock rate, right? Because that means that in one clock cycle, you have to get the instruction, get it through the control unit, and then into the ALU, right? You got to go through control unit and through ALU, and that creates a critical path delay that pretty much limits you to about 50 megahertz, which is what we have, right? If you want to make the clock faster, you got to pipeline it deeper, right? You got to add more stages. But again, we did this 3-stage just to make it as easy as possible, because there's already a very high jump from lab 2 to lab 3 is an enormous rise in difficulty. Okay, so then we have control. Oh, right. So here's the instruction. Yes.
Did you say to make the clock faster, you have to make the pipeline deeper, or is that IPC?
No, the clock rate. Yeah. Yeah, but usually there's a trade-off. If you make the clock faster, the IPC will go down because you'll have more branch penalty cycles as a result of having a deeper pipeline. But that's, yeah, that's a good point. Okay, so here's the instruction memory. So this part is really cool. I love this. In RARs, if you write a code in RARs and you assemble it in RARs, and then you say file, dump to file, and you select, actually it looks like this, dump memory to file. If you select the text segment, which is the default, and then you change this to hexadecimal text, this will actually save a file from RARS with the hexadecimal representation of your program in a format that is directly readable into the Verilog, just by coincidence. Just a coincidence that it just happens to work that way, right? Even though no one ever intended it to work that way. So the idea is that you write the assembly code in RARS, test it in RARS, and then dump it out of RARS, and it loads it directly into your hardware CPU, right? And it's done through this initial read memh line of code here, right? So basically, this will take whatever you, some people call it hexcode.txt, other people call it program.rom. The extension doesn't matter. The point is, it's just a text file with a bunch of 32-bit hex values on it, and it sucks this into instruction memory. And this effectively loads the program into your CPU. The only way to reload it once the FPGA is programmed is, well, there is no way. You'd have to reprogram the FPGA. Well, it's more than that, actually. You have to compile this. You have to synthesize this, which incorporates, as part of the synthesis process, this hex code into your bit stream, and then you program the bit stream on the FPGA, and that will load your program. There is a way to do in-place loading, which we used to do in this class, but no one ever used it. Everyone just felt it was easier. If they want to change the software, they just recompile the hardware, okay? So, but there is a way to get around that if you really want to. Okay, so we got the instruction memory is declared, instruction EX is declared. We load the instruction memory here, and then there's the fetch stage, basically. Just always at FF. If you're resetting, reset. Otherwise, just increment the PC. Notice if you reset, it also clears the instruction. That's important because otherwise you got a problem. Because if you reset and then you just reset the program counter, then you've already got at that point an instruction in execute, right? So there's nothing you can do about that unless you clear the instruction at the same time, right? Now, Alex learned the hard way, actually, that this synchronous reset is actually not a great idea because it actually creates the critical path delay. It turned out it's not the execute stage. It turns out it's the FPGA's resets are asynchronous. The FPGA likes asynchronous resets better. So it would probably be better to put a pause edge reset here as well. But it doesn't really, it'll still work at 50 megahertz either way. Okay, you guys with me? Does it make sense? Okay, so moving along here. So now we're going to talk about the EX stage and the write back stage. So the reg file we give you, the ALU we give you, these boxes here are just always at pause edge clock, that equals that, right? So these boxes are one line of code that just clocks something. Clocking means delay it by one cycle, right? Because they're pipeline registers. Yeah, that's it. And then the muxes, what is the mux? Well, the mux is just an assign with a ternary, right? Remember we covered that. That's what you use the ternary. You know, you basically just, it's like an assign statement, a combination of logic. You can use an always com for that if you want with an if statement, but I find it easier just to use an inlined assign statement for the muxes, right? Now, the only thing in here that you really have to build that's complicated is the control unit. The control unit, its job is to resolve the control signals. What are the control signals? Well, there's not many. It's actually very simple. We've got reg write, EX. Reg write determines whether you're going to write a register or not. Why do we need that? Why is that a control signal? Because not all instructions write a register. Most of them do. Almost all of them do. I think the only one in this lab that doesn't is the CSRW, right? I think that's, and even then, only if you are writing the hex displays, right? So most instructions will have reg write EX to be 1, most in this lab. Once we get to the next lab, obviously branches won't write a register. Branches don't write a register. Well, you can say they write the PC, yeah, but they don't write a general purpose register, right? So reg write EX its job is to distinguish between an instruction that wants to write a destination register and one that doesn't. Then there's reg select. This one determines what register you want to put in the register file when you write it, or if you write it. If you're not writing it, then this guy's a don't care. You can assign them to whatever you want, right? But if you are writing a register, then this guy controls a mux over here that determines what gets written. You have 3 options. Option 1 is whatever's on the switches. When do you do that? When you do the CSRW instructions, when you ingest the switch values, the input from the user, right? Basically, the idea is that user flips the switches, and you need to get those into a register, and so you select that mux to be 0 when you're executing that instruction. The second option is basically the 20-bit immediate value from the load upper immediate, which has to be 0 padded. The lower 12 bits have to be 0 padded, right? And option 3 is whatever the ALU is producing, which is going to be used in the majority of your instructions, because normally when you write something, you're writing a number crunched value, a computed value from the ALU, right? But it's not always that way, right? It's just most of the time. So you have to have that selected. Now notice though, this reg select is registered here. It's delayed. Why is it delayed? Because we want to push that into the write back stage. So that's one of the things I forgot about. In the write back stage, that register, that mux is in the write back stage. So everything before that mux goes through a pipeline register, just a set of delays, right? And again, these are just one line of code, you know, just always at just clock logic, right? Makes sense? So the ALU will produce something called R, right? The result. It produces it in the EX stage, but then you clock it to push it into the write back stage. So this write back is going to be whatever the EX was in the prior cycle, right? That way you can delay whatever comes out of the ALU and you can defer it so it gets actually used not in the execute cycle, but in the write back cycle, right? Because we don't want to have to write back. I mean, we're doing enough in EX, right? We're going to defer the write backs until the third cycle of execution. Okay, likewise, GPIO in. Now this one's kind of dumb because GPIO in is controlled by the user flipping switches. And so basically, if the user has the reflex to change the switch values in 1/50 millionth of a second, then this register will make a difference, otherwise it won't. So this is kind of asinine and redundant, but we still technically assume that the GPIO is coming in during the execute stage. But in truth, you don't really need this register. But this one here is this one's important because this register is taking the 20-bit immediate from the U-type instruction and moving that into the write back stage. So all of these are critical except for this one. Okay, does that make sense? Okay, and then finally, let's see. Finally, we have the I-type path. So basically, for the I-type instructions, you're just adding a mux in front of the B input on the ALU, because the ALU normally just operates on the 2 register operands. But if you do an I-type instruction, you have to bypass the second register and send in the immediate value, which is a 12-bit, has to be sign extended, obviously, because the immediate is 12 bits and ALU expects 32 bits, so you have to sign extend it. This is a difference from if you guys remember MIPS, MIPS had a unsigned, with MIPS you had a 0 extend or sign extend depending on if you were doing a signed or an unsigned immediate. In RISC-V, everything is sign extended, so they simplified this, right? Make sense? So in RISC-V, in MIPS, if you did an OR-I instruction, or meaning, you know, the bitwise operator or immediate, the MIPS guys were like, wait a minute, you can't sign extend that because there's no sign bit when you do a logical OR, right? Sign bits are for arithmetic, like add and subtract. So they would 0 extend that. But in the case of RISC-V, they sign extend everything. Okay? All right. So then there's an ALU source that controls that register too, right? ALU source would be 0 for R-type. It would be 1 for I-type. Right? So the control unit just has to decide, is it an R-type or an I-type? Nice, change the ALU source based on that. GPIO write enable. So this one is controlling the output to the hex displays, to your hex decoders. Okay, so this is a register, I think it's the only register with an enable on it. Because the idea is when you have the CSRRW instruction, you're going to update the contents of that register. And then you want to hold them. So this is a common mistake that we see, is that you want to make sure that whatever you put in that output gets held, because the actual values that you push out to the hex displays are only going to be generated in one cycle, right? So if you don't have this as an enabled, what will happen is your hex displays will only reflect the output for 1/50 millionth of a second, and then will basically just go to 0, right? Or whatever's coming out of what happens to come out of the register file, right? This is the most common mistake we see in this lab, by the way, is that students will design this lab and then they run it and they just get zeros and like, what's going on? It's not working. Well, because it is working, but you're only seeing the result for a 50 millionth of a second. By having this be an enabled register, you can capture the output for the hex displays and keep it there until the next time you want to update the hex displays. Does that make sense? So remember, I showed you some stuff in the last lecture about enabling. You basically just, it's always a pause edge clock, but you put an if statement in there for the enable, right? Okay, so that's pretty much the whole CPU. And so so what I showed you before was, I tried to break it down into pieces, but this is the whole thing put together. So this is the entire RISC-V CPU in one PowerPoint slide, at least one that executes the, I don't know, 20 instructions or so that we're implementing, right? And again, the reg file, the control unit, the reg file and ALU are given to you. The instruction memory is actually not a module, it's just basically a line of code, right? Even though I showed it as a module, I made it a box that's blue, implying that it's the same thing like the register file, but that was a mistake. This is just like a line of code, essentially. But you can make it a module if you want. Some people like to make the instruction module its own, instruction memory its own module. Yeah, and then everything else is pretty much, these boxes are always at pause edge clock, muxes are assigns, and the sign extend is just a bit duplication line in Verilog. So you have everything you need to build this. It's just a matter of figuring out how to put everything together, right? So the next question is, oh yeah, let's go through some examples here for the control unit. Yeah, I think this is kind of helpful, hopefully. So the control unit is a lookup table. But in Verilog, you can build a lookup table just with an if statement, if then else, right? And what ends up happening is the if then else is automatically converted to a table. But by making it an if then else, you can make it more readable, and you can also encode like don't cares and priority and that kind of stuff, which is part of the syntax of the if then else, right? So basically what you end up with is a lookup table where you have 4 inputs in total. There's func 7, immediate 12, which as I mentioned is only relevant for CSRW because they put the control register in the immediate field. Func 3 and opcode. Okay, which means that effectively there's 17 bits of control information at most in an R-type instruction. There's less different fields in an I-type, right? But in R-type instruction, they have 17 control bits, not including the immediate, which is something specific to this class. Okay, meaning, by which I mean, by having access to those 17 bits, you can figure out how to set all the control signals to set up the CPU. Okay, and what are the control signals? Well, there's only 5 right now. ALU op, which tells the ALU what to do. Remember, there's 13 different things the ALU can do. It's defined by a 4-bit signal, ALU op. ALU source, which is basically very simple, just 0 for R-type, 1 for I-type. And it's a don't care for U-type because U-type uses that reg select to bypass ALU entirely, right? Reg select, which is essentially almost always 2, except it's 0 for CSRW for the switches, and it's a 1 for LUI, right? So that's pretty straightforward. Reg write is 1 always, except for CSRW writing to the hex displays, right? I think some students in this class will set that to 0 for a no-op instruction, but you don't actually have to because a no-op instruction is kind of harmless because even if it writes a register, it just writes the register 0, which has no effect. Then there's GPIO write enable, which is always 0, except for one case when you're writing to the hex displays. So these are, so for example, now notice that I've added this column instruction because I don't have this stuff memorized. I don't know what the codes are for all the different instructions, the control codes. So you have to get this from a table on that's in the lab sheet and also available on Dropbox. What's it called? Blackboard, right? There's a document. So for an add instruction, the func 7 is 0. The func 3 is also 0. And the opcode is 33 in hex, in 7 bits. Well, hex is 7 bits. You might say 2 hex digits, that's 8 bits. Well, Not really, because as long as that first digit is less than 8, then it can be 7 bits, right? That makes sense? So what do you do? If it's an add, what do you do? Well, the ALU op should be add, right? Whatever the code is for that, which again, oh, I have a table here for that too. So what's the ALU op code for add? 0011, right? ALU source, what's that supposed to be? 0, because it's R-type, right? You're adding 2 registers, you're not adding a register and immediate. Does that make sense? You guys remember add immediate, right, from 212? Okay, that's when you add just a constant. Reg select should be a 2, because 2 means write the output of the ALU. Reg write should be a 1, because obviously we're writing, the whole purpose of this instruction is to write a register. And GPU IO write enable should be a 0, because it's not, we don't want to update the hex displays. So, yeah, actually I did it by column, right? So ALU op is an add is 0011, subtract is 0100, that's from this table. You can also look at the Verilog too for the ALU if you want to find these codes. It's just an if then else statement. Or no, it's a case statement? It might be a case statement. Whatever, it's obvious in the code. Multiply is 0101 and set less than is 1100. You remember the set less than, how that works? Set less than is, compares 2 registers and it just writes a Boolean value to the register, 0 or 1. Okay, ALU source is going to be 0 for all these guys, right? Because they're all R types, right? So that's all 0. Right, reg select is going to be 2. It's going to be 2 because they're all ALU, 2. Reg write is going to be 1 for all these because they all write a register. And GPIO write enable is going to be 0 for all these because none of them are writing to the hex displays. Okay. Now, if you get over here, now we have an and I. So the difference between these two guys will have the same ALU op. The only difference between these two guys is ALU source because one's immediate and one's not. So you can see that here. See that? ALU source 0101, 0 for R type, 1 for I type, right? That's the, and then reg select is going to be, again, going to be 2 for all of them because they're all just consuming ALU stuff. Reg write's going to be 1 for all of them because they all write a register. And GPIO write enable is going to be a 0 for all of them because none of them are going to hex displays, right? Okay, then we get to some weird ones. So load up or immediate, ALU op is a don't care, it doesn't use the ALU, right? The goal of RISC-V is to have your hardware as utilized as possible, right? Your utilization should be high as possible. You don't want a case like LUI that the ALU doesn't serve a purpose, but it's unavoidable sometimes. So the ALU op is a don't care. Now, how do you set a don't care in Verilog, by the way? You use X. You don't have to, though. Usually in this class, everyone just uses 0 instead of don't care. You don't really get a lot of benefit from actually specifying. I mean, you guys remember from 211, if you have a don't care, you can use it to simplify the logic circuit, right? But I don't know how much the synthesizer actually does that. I'm not sure. I don't really have a way to measure it, but the impression I get is that they don't really, but I would, if you put don't care, it can help you with debugging because then you can see the don't care on your waveform and it shows up like as a dotted line. And so you'll know, hey, that must be ALU's not used in that cycle, right? Also, these two guys, neither one of these guys use ALU either. So it's actually always a don't care in this table. ALU source is also don't care. None of these guys use the ALU. That's useless. Reg select, now that's the critical part. Reg select is going to be a 0 for LUI. Why is it a 0? Well, because if you trace the wire, right, there's your immediate. Oh, I'm sorry, not a 0. 1. Sorry, I'm wrong. There's the immediate. It comes in, it goes down, and it goes into input 1, right? So for LUI, the reg select is a 1. Right. And then for these guys, it's a don't care for, which one writes a register? Switches, right? For switches, it's going to be a 0, and for this guy, it's a don't care. Why is it a don't care? Because if you don't write a register, then I don't care what the reg select is, right? And you don't write a register for the hexes. I mean, you might say, wait a second, you are writing a register. You're writing the GPIO out register. Yeah, but that's a that's a flip-flop register. That's not an architectural register. It's not a numbered register from like RISC-V register. It's like a I don't know why they call them. They're both called registers technically, but it doesn't write a architectural register like an assembly language register, right? So you don't. This guy doesn't write. And then yeah. So let's just fill that in, right? So ALU op, as I mentioned, always a don't care. ALU source, always a don't care. Reg select is a 1 for load up or immediate. It's a 0 when you're sucking in the switch values into the register file, and it's a don't care if you're writing out to the hex displays. Reg write is a 1 unless you're writing to the hex displays, in which case it's a 0, and the GPIO write enable is only 1 if you're updating the hex displays. Okay. Now, one thing I want to point out is what was it? I forgot. Oh, notice in this design, I mentioned the idea of changing the names of signals. So if you look at the way I labeled these, I originally made these designs before I knew how to, well, I knew how to rename signals, but I didn't know to rename the signals. So you see how I say instruction EX31 down to 12, right? That's the 20-bit immediate field. But if you rename it, you wouldn't use that. You would just say immediate 20EX, right? If you renamed it, right? So I have two names here, right? So like, for example, instruction EX bits 11 down to 7. What is that? Well, that's the destination register. But if I had renamed it RD_EX, I would just use that name, right? This is the smarter way to go, right? I was a dummy for trying to remember all those bit fields. I thought I'd memorize them, but I never did, okay? All right. Okay, so this is the complete table from everything I showed you, but it is not the complete table for the assignment because this is only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 instructions, and I think there's 20 or so. So I didn't give you all of them. You have to figure out the rest of them, but most of them are R types and I types that follow the same pattern. Same values, just different ALU ops. So the control unit will be an if-then-else that will implement this table. So how do you convert a table to an if-then-else? Well, that's what we want you to figure out, right? That's the goal. Figure out how to convert this to if-then-else. Or you could just build it as a big case statement or something possibly, but that would be ugly, right? Okay. All right. So how do you test your CPU? This is the hardest part. How do you test a CPU? I don't actually know how you test a CPU. Sometimes companies don't test their CPUs very well, and it leads to bugs. The most famous of which is the Intel floating point divide bug of 1996, I think it was. They used to have a facility in Columbia designed to test Intel chips, and they closed it. They used to hire a lot of our students. But how do you test a CPU? I don't know, because how many programs can a CPU run? Lots. I can't even, because it's not just how many unique instructions, but it's how many unique instructions and unique parameters and instruction orders, because remember, you have to consider forwarding and bypass and everything else. It's uncountable how many different programs you can execute, even on this simple CPU. At the very least, and like I said, I don't know the answer. I don't know how to test a CPU. I have no idea. But at the very least, you want to test each one of the instructions at least once, right? Now, technically, you should test them more than once because you want to test ones with a dependency between two instructions and with no dependency, and with different variations of the instruction, but at least once. So we gave you a test program here that will test each instruction at least once. And it starts out with these add i's with register 0. This is what seeds the initial value, like initializes register 1 and 2, and then all these instructions are kind of built off of that, right? The answers are in the comments. So the expected update to each one of these destination registers is in the comments. Now, how do you write a test bench for this? You can't, basically, because a test bench if you wrote a test bench, it would have to wrap around the CPU, and there would be no way for that test bench to look inside the CPU to see what registers are being written. It's impossible. Unless, of course, you export your one thing you could do is you could export your register, like you could expose your register inputs to the outside. Like you could take your register file and declare those signals that connect to it in the module line, which would expose them. But in reality, real CPUs don't do that. Everything is, the registers are hidden inside. They're under the hood, right? So how do you test this thing? Well, one way to do it, I know the way that Alex likes to do it, is he takes advantage of the CSRRW instruction where he basically says, I'll test an instruction and then I'll immediately turn around to the hex displays, which will expose it to the outside world, because anytime you do CSRRW with the hex displays, it gets spit out, right, outside the CPU. That's one option. However, you're not just testing one instruction if you do that. You're testing at least two, because you got to do something, actually more than two, because you have to initialize registers, then have an instruction that you're testing that operates on those registers, and then the CSRRW. And the error could be in any of those instructions, and you won't know which one it is, right? But you will know there's a problem, right? So that's one option. Another option is, in fact, that's how, I think we do require a test bench though for this lab, right? So you are going to have to do something like that. So you have to come up with a plan for this lab, technically. So you can either expose your register file controls or you can do the Alex approach. But as you're testing it in QuestaSim, you can actually plot the register file contents in QuestaSim and literally watch them evolve over time. So if you take this program, run it through Mars, generate a ROM file, and then simulate your CPU with this ROM file in QuestaSim, just dump your registers to the waveform and you can see them populate with these values in turn. Eventually, they may stop populating, in which case you know which instruction is bugged. Whatever instruction was the last one that was supposed to be populated that wasn't, right? When I say populated, by the way, in the register file, all of the values will be X's until they're written. And you might say, wait a second, I thought you said that the memories are initialized whenever you program the FPGA. Yes, but QuestaSim doesn't know we're using an FPGA. QuestaSim is assuming an ASIC. So QuestaSim is not going to initialize your register file to zeros as it actually is on the FPGA when you program it. So when you look at your registers in QuestaSim, they're going to start out as red lines, and then as the program runs, they'll get set, right? In like, I don't know, 40 consecutive cycles, they'll fill in. You guys with me? Okay, so that's a test program, and we want you to run this to test. However, this is boring. This is really pointless and boring. Painful even, because it doesn't do anything useful. So what if we want to do something useful? So this is the next test program is one that we want you to write in assembly. And it does something meaningful. What it will do is it'll take the switch values and convert them from binary, which is what they are, the binary, because there's binary switches up or down. It'll convert them to decimal, base 10. And then we'll display that decimal value to the 7-segment displays. So in lab 2, you guys, could put all the switches up, and then you would get like, some Fs, right? Once, like if you put 4 switches up on the 4 rightmost switches up, you'd see an F, right? Because what is that? 15. But it's hex, right? But I don't want to see it. I don't want to see F. I want to see 15. I want to see 1, 5, right? So the only way to do that is to have some kind of intelligence that takes the switches and does a conversion, a base conversion, right? So we want you to write a program that does the base conversion, right? So how do you do base conversion? Well, you basically just take a number and you do modulo by 10. That will give you the rightmost digit. And then you divide it by 10, which will delete the rightmost digit. And then you do another modulo by 10 to give you, which is the new rightmost digit, which is originally the second to the leftmost, right? And you just repeat this, right? Now you might say, well, wait a minute, we don't have modulo and we don't have divide. So that's a problem. Yes, but because you're dividing by a constant, you can simply multiply by the reciprocal of that constant. And we do have multiply. And modulo, this is I'm kind of proud of this, right? So modulo is if you use fixed point representation and you if you multiply by 0.1, right? So say you have a number like 12. If you multiply it by 0.1, which means you're dividing it by 10, the answer is going to be 1.2, right? That 0.2, that's the modulo. That's what you need to recover. But you can't, 0.2, what's 0.2 going to be? It's going to be 2/10 of the range of your integer value, right? Of your fractional bits, right? You have fractional bits, right? So 0.2 will be 20% of the dynamic range of your fractional bits, right? But if you then multiply that by 10, if you isolate the fractional part, 0.2, right? And you multiply it by 10, you can recover the modulo, right? So if you take 12, you multiply it by 0.1, get 1.2, then you take the 0.2, you take it off, and you multiply by 10, you get the 2 back, right? That's your modulo, right? Does that work? Well, the problem is that we have limited precision. And there's going to be some rounding going on, right? So it might not work if we don't have enough precision. So we want to maximize the amount of precision. So the way that that always worked for us. Okay, yeah, I already talked about that. I talked about that. Okay, yeah. So the way that works for us is, right. The way that always worked for us is the 0.1, I think I showed a demo of this in class, right? I did a RARS demo of this. The 0.1 can be represented in 32 bits that are all fractional. So the 32-bit value gives you 0 to what? To 4.2 billion, something like that? 2 to the 32nd power, right? So if you take the 4.2 billion and you simply divide it by 10, right, then it'll be 0.1 in fixed point, assuming all fractional. You guys with me? So basically, it turns out to be 429 million something, and then you have to round it. It's not an integer. You have to round that 0.10 up or down depending on which way you want to go. You guys with me? So you get the 0.1 in fixed point. Then you can multiply it by an integer with 0 fractional bits, right? And the result of that will be 64 total bits where 32 are fractional and 32 are non-fractional, right? You guys with me? What I'm saying is that you have two 32-bit numbers, one of which has 0 fractional bits. Another one has 32 fractional bits. When you multiply them, the product will be 64 total bits with how many fractional? 32, because you add the fractional bits together when you multiply, right? So the nice thing about that is those fractional and non-fractional are aligned on the decimal point. So basically what I'm telling you is that when you do the multiply high, you get the divided by number. When you do the multiply low, you get the fractional number, which then you can subsequently multiply by 10 and recover the original modulo by multiply high. Does that make sense? So the idea is that you basically just multiply by 0.1 in fixed point and then recover both the quotient and the remainder. Of course, it is an estimated. It's not going to be perfect all the time. But we've never seen an error though, right? It always works out for us, right?
Yeah, I've never seen that.
Yeah. So in other words, the conversion, I've never seen a case where it somehow had a rounding error or something. It's always worked. You guys with me? And it should, because you get 32 bits of precision, right? It should be enough.